Exact pairs for the k-trivial Turing degrees.
Thank you. I'd like to thank the organizers for inviting me. And I would like to talk today about a problem about the class of k-trivial sequences. These are the sequences which have trivial initial segment complexity, which has been around for a number of years. And this is joint work with Rod Downey. It's a problem with that I've worked since about 6 years ago, but we only solved it a few months ago in the Turing year, and part of the work was done here in the Institute. So let me state the problem. It first appeared in print in 2006 in a survey, an open questions paper in the Bulletin of Symbolic Logic by Joe Miller and Andrew Nees. And since then it has featured in a number of conferences, particularly in talks by Andrew Nees. And the most recent mention was in the Overwolfach meeting in a few months ago in 2012. So let K denote this class of k-trivial sequences and also their degrees, the Turing degrees. And the question is, does this set of degrees, which in fact, as we'll see later, is an ideal in the Turing degrees, does it have a C exact pair? So what does this mean? It means whether it can be defined as the set of degrees that lie below 2 degrees, which are like parameters. So the question is, are there C, A, and B Turing degrees such that the degrees in this class, the k-trivial degrees, are exactly the ones that are below both of them? Okay. So let me give you a brief introduction into the trivial sequences. They were first introduced by Chaitin in the 70s, and the first results about them were by Chaitin and Solovey in the 70s. And in the 1990s, Zambella worked on them, and then from then on up to 2005, there was a lot of work done by Downey, Hirschfeld, Stefan, and Nees, amongst other people. So we work with prefix-free Kolmogorov complexity K in order to define this notion of triviality, and the technical definition is X is k-trivial if and only if this is a restriction symbol. Okay. If and only if there exists some constant such that the initial segment complexity is modulo that constant is the same as the initial segment complexity of a sequence of zeros of the same length, or you could say n itself, the length itself. Okay, so these sequences, from the point of view of prefix-free complexity, they are as simple as an infinite sequence of zeros. Yet they can be incomputable. K-trivial sequences, surprisingly, they're downward closed under Turing computations. This is a result by Hirschfeld and Nees. And as a result, also closed under joint, they form an interesting ideal in the Turing degrees. So if you think about it, Turing computations do not map segments to segments of the same length. So it's not at all obvious that this notion is preserved by Turing reductions downward. Okay. That was quite a surprising result. So let's see some more details about this ideal. It is generated by C members. So this means that k-triviality is a C notion. Okay, you cannot construct k-trivials by forcing. In particular, given any k-trivial, although it may not be computable or even CE, there is a k-trivial which computes it, that is C, okay, computably enumerable. And as Dan mentioned in his talk, these degrees contain very low information. They are contained in the low degrees, which means their jump is the lowest possible jump. It means that sigma 1 sentences with k-trivial parameters are basically delta 2. And they're even super low, if you recall the notions introduced by Dan. And they have, in fact, an exact pair. And this exact pair could also be chosen to be delta 2, so below 0 prime. And this follows by some results offshore and some some facts about the k-trivial degrees. For example, that there is an incomplete upper bound for the idea of the k-trivial degrees. Okay, so that's known. So then the next question was, is there a C exact pair? So this is basically a definability question about the ideal of the k-trivial degrees. And in fact, in the BSL paper I mentioned before, there are a whole bunch of definability questions about k-triviality and multi-law randomness. So let's see what we're looking for. And there is a reason why this question has not been solved so far, and it took a number of years. So there is a reason why it got solved now. And the reason is that the right tools and results that we used are very recent, in the last 1 or 2 years. 1 year, one of them is the last year. So let's see what we're looking for and why it's not a very easy thing to answer this question. So we wonder if there are 2 Turing degrees, C Turing degrees. So this is 0 prime. These are, you could say, these are the C degrees, or you could say that they are the degrees below 0 prime which are bounded by C degrees. It doesn't matter. And the k-trivials are down there. So we want a pair of C degrees which are above the k-trivial degrees, so that every k-trivial is below both of them. And on the other hand, they're not too high, in the sense that if something is below both of them, then it's down there. So it looks like this. So the lower cones, the intersection of the lower cones is exactly the k-trivial degrees. So when you try to think of this problem, maybe you first try to construct an exact pair, and then you have to consider what happens in general with ideals in the Turing degrees. And the fact is that it's very easy to construct ideals in the C Turing degrees which do not have an exact C exact pair. It's a finite injury construction. They can be principal or non-principal, and the construction is quite flexible. So when you try to construct an exact pair for this ideal, you immediately have to deal with problems that arise from these kind of constructions, which in degree theory they're called non-branching constructions, because basically if you construct a principal ideal without an exact pair, then basically you're constructing a non-branching degree. So the next question is, how do you deal with these problems? On a technical level, there are very specific methods in which you construct non-branching phenomena, and these crop up in this kind of problem as well. And the immediate reaction is you use the actual properties of the k-trivials that we know in order to deal with them. So there was a hope like that, but in fact the whole thing gets too complicated, and in fact it's not easy. In fact, it's impossible to deal with these problems. So then we might try the other direction and try to show that there is no exact pair, C exact pair for the k-trivials. So how would we do that? Well, maybe by contradiction, right? Assume there is one. So these 2 degrees are above all of the k-trivial degrees. Then you want to construct something below both of them, which is here, okay? But how are you going to do that? You have to use the hypothesis. You have to use that both of them are above all the k-trivial sequences. Now, there are infinitely many k-trivial sequences, and also you can't just test this hypothesis by constructing a finite amount of k-trivial. So my main point here is that there is some aspect of non-uniformity in the construction that is very hard to deal with. And that was the main problem. If you try to write out the requirements to satisfy these conditions, you probably won't. At least the people who tried this problem all these years couldn't. Okay. So in this kind of situations, it's quite probable that you can reformulate the problem to something simpler, but probably stronger. So prove something stronger that is easier to prove. Okay. And that's what we're going to do. So here is a suggestion. Maybe given any pair, if there was a C exact pair, this pair would be non-k-trivial degrees. We know that. So maybe we can just take that and use just this and not the whole hypothesis. So maybe we could show that given any 2 k-trivial degrees, we can construct, so non-k-trivial degrees, we can find a non-k-trivial degree which is computed by both of them. But in fact, you can't do that because there are minimal pairs of k-trivial degrees. So the next step is maybe you can do that with the help of another k-trivial degree, right? So given a pair of non-k-trivial degrees, you can find a k-trivial degree such that the join of this with the 2 actually computes something which is not k-trivial. Okay. Not only we will succeed in this, but we will prove a uniform version. So there exists exactly one. No, there exists a single k-trivial degree which does this job for any possible pair. So let me show in pictures because I talk too much without pictures. So there exists one k-trivial degree such that for every pair of non-k-trivial degrees, everything you see here, the joins compute a non-k-trivial degree. Okay. So this means I had a discussion with Andrew before. You can express this in terms of the quotient structure of the C degrees modulo the k-trivial degrees, and say this structure doesn't have a minimal pairs. That's what it says essentially. So if you have k-trivial information for free, then the resulting structure doesn't have minimal pairs. So for every pair, non-trivial pair, there exists something non-trivial below both of them. So let's see that again. There exists one k-trivial degree such that for every pair of non-k-trivial degrees, the joins compute something non-k-trivial. Can you see that this is enough for what we want? It's much more than enough. Because if this was an exact pair, it would be above all k-trivial degrees. So the joins would actually equal A and B. So this computes something which is not in the ideal, which means it's not an exact pair for this ideal. So that's the theorem. Okay. I just said it. So it turns out that the non-uniform version, so for each pair to construct a separate D, k-trivial degree, is as easy as the uniform version. So why not do the stronger result? So this implies that the answer is no. There is no C exact pair for the k-trivial degrees. And this prompts to branching constructions in the Turing degrees, only that on a technical level, the methods are completely different. Okay, because non-triviality for us is not k-trivial, but for classical degree theory is non-computable. Okay. So I'd like to say a few things about the ideas behind the proof, because so far I haven't said anything. So basically, that's me saying what I've been saying for a number of years. Every pair of C degrees which are not k-trivial have common information. And I have expressed this in a number of different ways. And in fact, you can see this result, the one I just presented, as just another formulation of this. I will explain why. So you cannot say this for strong reducibilities in particular. You can't say it for Turing reducibility because there are minimal pairs of Turing degrees which are not k-trivial. So anything computed by both of them is in fact computable. So it's trivial. So but for weak measures of information, relative information or complexity, it is true. For example, they see k degrees. So this is when we compare the initial segment complexity of two reals, segment by segment. So one is k below another one if for all n the initial segment complexity of the first one is less than the one of the second, modular constant. That's the k degrees. And for the c k degrees, there are no minimal pairs, which means that if you have two reals which are not trivial, they don't have trivial complexity, then there exists something that has less complexity than both of them, but still non-trivial. Okay. So this is an indication that if you take any pair of non-trivial sets, then you can find common information for the k degrees. And the same holds for another measure, the LK degrees, which I'm not going to define, but they measure the power of an oracle that an oracle has to compress finite sequences. And in fact, here you can prove it for a larger class, delta 0, 2, that there are no minimal pairs. So that every pair of non-trivial degrees has common information, something common below both of them. Okay. For the k degrees, that's open, whether it can be extended to delta 2. Okay. So we are going to use this formulation of this claim in order to derive what we want. Okay. At this point, it may not seem very relevant, but if you think about it, look, what this says is that get any two non-trivial c degrees, which for us is non-k-trivial. Then they have non-trivial information with the help of a fixed k-trivial degree. Okay, we said Turing is too strong to assert this, but if you have the k-trivial degree, it's for free, even a single k-trivial for free, this one, not any, then it's exactly what it says. And I realized this connection about a year before we solved the problem, which means it's not an immediate corollary of this. You need to do a little bit more work, but I think now it's clear that it's more or less the same thing. It's just another formulation of all the other results and this intuitive claim here. So I won't bother you with many technicalities. The paper is not very long, it's just 13 pages. And the proof is very modular. So I just want to describe the structure because it's modular. So what we want is derive a sufficient set of requirements which actually which we can satisfy. So in a pretty much standard way. So we want a sort of standard cost against cost construction. So remember, we are constructing a k-trivial set, which means we cannot put too much complexity into the set. So we have our own cost of enumerating. But the opponent also has a cost. when he wants to sort of insist that the requirement is not satisfied. So the final requirements look like that. If there are many opportunities where we can hit cheaply, so our cost is low, but his cost, recovery cost, is high. So if there are such opportunities, then we meet the original conditions. So this is a pretty much standard construction, okay? But the novelty of this proof is not in this construction, is why do we have these opportunities, okay? And this is where we use the result that any two C sets have non-trivial complexity. So that's the final part of the construction, but in fact, a lot of the work is to prove that the actual requirements are sufficient, and in particular, we will have these opportunities, provided that the given 2 degrees are not k-trivial. So let me be a little bit more specific. The actual result we are going to use is this one, which is actually a corollary of what I mentioned before. So if you have any two CE sets which are not do not have trivial initial segment complexity, then it means for each of them the complexity will go up and maybe down. It could be infinitely often k-trivial, but not k-trivial. But what this says is there will be common points where it goes up simultaneously for the two sets. And that's, again, another formulation that two C sets which are not k-trivial have common information in some vague sense, because the complexity will go simultaneously up at some points. It has to go. And I'd like to mention that I don't know whether this holds outside the class of C sets. So it could be a C phenomenon. So is it possible to have two sequences where at any point one of them is k-trivial with a fixed constant? So when one complexity goes up, the other has to be down. So they go down like that. Probably not, but I don't know how to prove it. So that's an open question. That's the main result we use. And another tool from the last, Solovay functions, I'm not going to define them. They were introduced by Solovay, but studied recently by Downey and Laurent Bienvenu, and later Andrei Nissa and Merkel and some other people. And it's basically a technical tool that we use to simplify some calculation, but in fact, I have to admit, is quite useful. It simplifies a lot of things. And it's quite natural to use it if you look at the details of the paper. So I think this is what I have to say about the proof. I'd like to, I didn't mention this in my abstract, that's the second part of the talk. The other thing I've been doing the last few months is I'm writing a survey about measures of complexity. It's quite focused, so I'd like to present the focus of this survey and some implications we can make given the results we know so far. So the focus of the survey is what do we want to measure using all these reducibilities which are based on initial segment complexity. For example, one sequence is more random than another, or one sequence can compress more efficiently than another when it's used as an oracle. And more importantly, we want to highlight situations where we have two measures, different definitions, two different measures that are supposed to measure the same thing. But in fact, they're not only they're not equal, but they behave very differently. So that's a problem. If you have two measures and you claim they measure a single thing and then they behave very differently, then this raises issues. So the main point of the survey is to highlight these kind of situations. And I will be more specific. So the main question, we want to raise some concerns about this issue. Do the measures reflect the intuitive notions they are supposed to represent? And if we come across to situations like the one I just described, then this raises some issues. Okay. Let me be more specific. If you want to separate two classes or two measures of complexity, the most common way, or the first thing you try, is artificial brute force separations by diagonalization, priority, forcing arguments, and so on. And for example, a number of these concerning the measures we are looking at were done in a paper by Downey, Hersfeld, Lafort, and Stefan, and Merkel later. No, sorry. I don't. Okay, I take this back. Remove. Okay. So why do I call them artificial? Because suppose you wanted to separate two measures, then you have to construct. You have to design specific parameters where the equivalence breaks down. But that's quite artificial, because you sort of engineer the whole situation in order to achieve what you want. Okay, it's not like these kind of results do not point to intrinsic difference between two measures. So if you have such a result and only such a results, and you ask, are these measures really different? I mean, do they behave? Then you don't have an answer. But there is a stronger way to separate measures, and then this is the discovery of elementary properties that hold in one measure but not the other. So this kind of result raises serious issues, especially if the two measures are supposed to measure the same thing.
What's the paper without Merkel show?
Sorry?
What's the result in the paper without Merkel?
Oh, many results, like separations of this C reducibility, K reducibility, RK, Solver reducibility for the relative randomness.
You mean measures, not measures on Cantor space or anything, but measures to gauge randomness or calibrate randomness?
Yeah.
The measures in a different
Yeah. Yeah.
Okay.
Measures of complexity. So so we're not interested in these kind of separations in this survey. I mean, we at all. We don't discuss any of this. We're interested in this kind of separations which raise the issues I just said. So let me be more particular here. An example. Take the plane complexity and the prefix-free initial segment complexity. So let me remind you, plane complexity is when the underlying machine which gives the descriptions is a simple Turing machine. And here it has to be prefix-free. And the difference is basically that if you use a normal Turing machine, then you say that the complexity of some sequence X, complexity. So if you have the sorted description, is actually this number of bits. You have an additional additive factor, which is the information you code in the length. So that's a fact. So if you use plane complexity, you actually say, actually the complexity is only this one, and you ignore that. But that's an additional information that makes a difference. So in this way, prefix-free complexity is a more refined measure, where you say you don't allow the machine to use this information, and you say the complexity of X is equal to this. Only. So if you want to say the number of bits is of the sorted description is the a good measure for the complexity, then a prefix-free complexity is more refined. Anyway, you could say, and maybe there are some objections, but you could say that these two measures are supposed to measure the same thing. Mainly, so in particular that the initial segments of A are less complicated than the initial segment of B. Just that you have two different formulations, the prefix-free and the plain one, the other way around. Okay. So let's see, we know that these two are different.
What about
the other 3 or 4 notions of complexity?
Yeah, we present a number of results, but I want to focus on a particular example.
I mean, but those also could be. I mean, you could ask these same questions for them.
Sure. Yeah. I just want to be very specific now and give you a separation of this kind for. Now you mentioned, for example, take solver reducibility. What I'm going to say now holds for solver reducibility in place of C reducibility. Okay, so you get 2 separations, but I don't say it in the slides. Okay, so solver reducibility is a standard measure of relative complexity in the C reals. Okay, and we'll see. Okay, here is a statement. It says that that could refer to any measure. Okay, every C set can be split into 2 disjoint C sets of the same complexity. Okay, this statement is false in the Turing degrees. This kind of phenomenon is called non-mitoticity in recursion theory. There are many C sets which do not have this property. So how about the 2 measures we mentioned? For plane complexity, it doesn't hold as well. And the reason is that you can easily translate results in the Turing degrees to the C degrees. Because if you take a very sparse set, like powers of 2, then the 2 reducibilities are essentially the same. So if for you the complexity means plane complexity, plane initial segment complexity, then this is false. So there are C sets that any way you split them in 2 disjoint C parts, they will at least one of the parts will have strictly less complexity. Okay. How about prefix-free complexity? Well, it turns out that no, it does hold. So that's a result in a recent paper by myself, Rupert Holtz, Andy Lewis, and Wolfgang Merkel. So that's a concrete example of what I was talking about. The same holds for solver reducibility in terms of in place of plane complexity. And this is the kind of situation where it raises some issues as to, arguably the 2 measures are supposed to measure the same thing, but this is quite a basic property, and the 2 measures behave entirely differently. Let me give you another example where let's look at the elementary theory in the degree structure. Okay, so maybe we can separate the 2 measures there. So given any 2 C sets or C reals of non-trivial initial segment complexity, there exists one of strictly less non-trivial initial segment complexity. So this is the lack of minimal pairs, basically. It's a 2-quantifier sentence. That's the lowest complexity of a sentence that could separate the 2, because one quantifier is decidable, is trivial. The theory is trivial. Okay. Again, for plane complexity, it doesn't hold, because it doesn't hold in the Turing degrees where we have minimal pairs. But as I mentioned before in the first part of the talk, for prefix-free complexity, it holds. That's the lack of minimal pairs. And that's a recent result by myself 1 or 2 years ago. So these are a small technical difference in the definition of 2 measures that are supposed to measure the same thing is reflected to an elementary difference in the degree structures of the lowest possible complexity, 2 quantifiers. Okay. So I'd like to sort of conclude by sort of advertising another result from my paper with Rupert, Andy, and Wolfgang Merkel. which is we found that a strange phenomenon that there are C sets of maximum initial segment complexity with respect to all of the measures I mentioned, and some I didn't. So with respect to a prefix-free complexity or plain complexity, or even stronger. So these C sets have initial segments which are most complicated. So if you have heard something about Chaitin's omega, in the world of C reals, omega has exactly that role, that its initial segments are more complicated than the initial segments of any other C real, modular constant. Right? So omega is the number of wisdom because it's a maximum in the structure of initial segment complexity within its class. Right? And surprisingly, we have the same phenomenon in the C sets. So there are C sets, numbers of wisdom. That's quite strange because the initial segment complexity of C sets is quite low. Okay, but within their class, there are numbers of wisdom. Okay. So that was a bit counterintuitive. I was thinking of this question for a couple of years, and I asked a number of people, and the intuition was no, that's counterintuitive. For example, if you have heard about the Kummer gap phenomenon, it appears to contradict that, but it doesn't, in fact. Okay. So I'd like to conclude my talk with some references. The first paper is the main result that I talked in the first part of the talk, and you can find it on my webpage. And the second one is the result we used to get the first one, which is the lack of minimal pairs in the k degrees. The third one, so let me say, we thought a lot about how we're going to write this paper and whether we should incorporate this proof to make a self-contained argument or whether we should opt for the modular style. And we opted for the modular style because embedding this argument in there would be basically like adding the two papers together. I couldn't find a simpler way to do it. So I reread the whole proof there closely and tried to see if I can get a more direct argument here, but it wasn't worth it. So the third one is my survey. It's still in preparation, and the last one is the paper I mentioned, and all of them can be found in my webpage. Thank you.
Questions for George?
Yeah, so there was a definition of comparing the sets of A and B, measuring the complexity of initial segment with either K or C. But what happens if instead you require the conditional complexity of the prefix of A, given the prefix of B of the same length, to be small? This kind of, if you wanted to measure somehow, to try to consider infinite objects.
You mean the triviality notion with respect to this coincides with computable?
No, not triviality
Okay.
notion.
So just saying okay.
Oh, okay.
Okay, yeah. That has been stated. It's called RK. The complexity of A given B given A up to n given B up to n is a constant.
You mean, but maybe he means something different. You mean A given A up to n given n is
and B and B up to n.
Oh, he does mean RK. Yeah.
No,
Yeah, that's called RK.
But it's up to constant or up to logarithm.
Up to constant is RK, right?
Yeah, but it's probably more natural to look up to make no difference between K and C. Let's allow the O of log n.
Right.
Something is.
Yeah, for log n I have not looked at it, but for a constant, this result also holds for this definition. Or were you referring to this one or another one?
No, if it holds for a constant, it's even better.
Yeah, this holds for a constant.
And what is this C set? Can you explain how?
Yeah, thanks. It's a good question. I forgot to say. This is a new class. It appears to be a new class of C sets. They are all WTT complete. So they are in the WTT degree of the halting problem. But it's a proper subclass of the WTT C sets, the complete set.
No, but just how to construct one of them? The universal one somehow. Can you have a universal one which will be have maximum initial segment complexity?
Yeah, it's not a difficult construction. It's you have to you have to be very economical with your enumeration. So the main idea is that you wait for a certain amount of coding. So suppose you want to write. Suppose you have requirements of the type. You're constructing a universal one, and you have many requirements of this type. It should be more complicated than all of them. So for each index E, in order to code, to make a change in the first n bits, you wait for a number of changes there, say 2 to the E, something like that. But you have to manage it. With C sets, you don't have too much space. Once you enumerate something, that's it. You cannot change it. So you have to be a little bit more clever and sometimes enumerate at lower places. So this kind of construction is not compatible with increasing the complexity exactly. Suppose that you have two sets and you want to make one that has larger complexity than both of them. Actually, you have to make something slightly more complicated than both of them. In other words, you cannot achieve a join in this structure using this kind of technique. That's why questions like density in the C degrees with respect to this measure is an open question for us.
Can you say you have two sets A?
Yes.
You want to two sets A, and you want to construct one B so that the first n bits of B somehow encode both information for these two A1 and A2. Can you just give a hint how you do this?
It's a dynamic construction. It's not like it's a construction with a C construction with enumerations. So I cannot give you I look at the segments and I think maybe I should. No, it's a dynamic construction. So when
maybe you can just choose one of them which requires more time. So if you have this time bound, then you can generate other also.
It's a paragraph. It's not a complicated construction. It's like a half a page. But it's,
You have to arrange that the universal set converges only after the other set up to a constant number of places.
Oh, you do have quarter of an hour.
I know, but I decided I won't be too technical in this stuff. I don't know.
Okay.
Could you say why it doesn't contradict the Kummer gap?
Sure. Yeah. So the Kummer gap phenomenon is that you can have C sets have low complexity. The prefix-free complexity. Well, let's see. The plain complexity is bounded by 2 log n for a segment n, and the Kummer result is that there are C sets that achieve this upper bound infinitely often. Okay. So now the thing is that different C sets may achieve this upper bound at different places. But that doesn't contradict the result. I mean, why does it contradict it? I guess it's
I didn't know what
counterintuitive.
the bounds were going to be for this thing. I guess that's what it has. You have strings that go 2 log n for every initial segment. Is that what?
No, you can't have that.
No,
That's the theorem of Soloway. You can't have that.
you can't.
So what do you get?
The problem with Kummer construction is if you look at the construction, you can have these high complexity prefixes wherever you want if it's effective, but you need some space for that.
Right. So
it
you
could be
need
this
more
width or that
exponential
width and
space.
whatever, and then it does not look like you can have something with above all the widths. This looks not doable in a sense.
Yeah.
So how complex are these ones over here?
They have to be. In which sense?
In the sense of, what is the initial segment complexity?
For example,
What are they maximal about? Yeah.
The maximum is 2 log n and the minimum is log n. That's always.
Oh, that's just what we do.
It's false.
Yeah, but that's not. Then what's the theorem?
And that's another thing that's strange. They go down to log n at some places, but then all the other CE sets must go down to log n too.
Yeah.
This is a little bit weird, yeah.
It is weird, yeah. So I guess, yeah, modulo the constant that you assign to that C set. Yeah. It's a bit counterintuitive, that is true.
Any other questions? Were there, you mentioned compression power, reducibilities that have to do with compression power? Measures of randomness that have to do with compression power?
Yes, I meant the LK degrees.
Okay, okay. So what,
So
what
the
other
LK
things?
is, I say for everybody. So A, these are reducibilities that have to do with compression power. So B has more power than A. If for any program can be compressed better using B as an oracle than using A modular constant. Yeah.
And what are the results about those?
So I just this is just a sample of there are many differences like that. Now, all right, I didn't mention about this at all.
Elementary properties that are different?
Sure, yeah. For example, there are a lot of differences between. So LK is close to Turing reducibility because it measures the computational power of the oracle. So it wouldn't make sense to compare LK with I don't know, K or Solovay, not too much, because they measure very different things. So what we do in the survey is we look at measures that are measuring similar things and then separating them in a very dramatic way. So some results about LK and Turing are that differences in the elementary theory for the C structure or the delta 2 structure as well. And this is as low as possible. Again, 2 quantified sentences. For example, minimal pairs. I did mention it
minimal pairs
implicitly. It's a very, but there are more than that. And for all kinds of structures, including delta 2, C. Yeah.
All right, let's thank George.